Okay, in this video we're going to talk about volume. So in the past we looked at the area under a curve, and now we're going to take that area and rotate it around an axis to get a three-dimensional solid. So for this problem, find the volume of the solid formed by revolving the region bound by y equals x equals 0, and x equals 4 about the x-axis. So the region that we're talking about is right here. And if I rotate this region about the x-axis, I'm going to show you what I've learned over the years on the best way that I can do to make something look three-dimensional. I'll show you my method. So first of all, hold on. So here's the area we're talking about, and we want to rotate that about the x-axis. So it's going to rotate around the x-axis and create this three-dimensional shape. See if you can visualize, if you rotate that triangle around the x-axis, what shape this would be, what three-dimensional solid this would be. Okay, so let me show you how I draw this. The first thing I do, since we're rotating about the x-axis, I'm going to reflect the line y equals x about the x-axis. So I'm just going to reflect that to show that the fact that this is going to be rotated about that line. And then to make it look three-dimensional, here's my hokey little workaround. I just connect these 2 points with a circular arc. So now I'm going to take away my little shading because it doesn't quite fit. Now we got this cone. And we know a little bit about the volume of a cone already. Let's just look at this cone here. The volume of a cone is 1/3 the area of the base times the height. So in this case, 1/3 pi r squared times the height. And on our cone, the radius of the base is 4. And we also know that the height of the cone is also 4. So we can find, using the volume of a cone, we can say this is 1/3 pi, the radius is 4 squared, times the height, that's 4. 4 squared, 16 times 4 is 64. So we get 64 thirds times pi, or 64 pi over 3. So using geometry, we found the volume. But the shapes that we're going to be working with will not always be linear like this. It will not always form a shape that is something that you recognize. So I'm going to show you another way. I'm going to generalize this to be any shape with any function rotated. So I'm going to look at this and think about when we first were finding the area under a curve. We said that if we find the area of a rectangle, one representative rectangle, and we just integrate that over and over again, so add all of those rectangles together, we'll end up with the area under the curve. And we knew that the height of this rectangle was the function, because it depends. I mean, your rectangles, it just depends where you're at on the function and how tall that rectangle is going to be. So we found that the height of this rectangle was the function. In this case, that's x. And we said that the width of each rectangle is something really, really small. We said that was dx. So we're going to use that same idea. We're going to use that rectangle that we used to find the area, but we're going to rotate that rectangle around the x-axis because we need something that's three-dimensional. So if I were to rotate this rectangle around the x-axis, think about what shape that might create. I'm going to have to erase my rectangle because I don't know how to draw this without starting from scratch. So if I were to rotate that rectangle around the x-axis, I would end up with a cylinder. But what we're going to do, instead of finding the area of one rectangle and adding that together, we're going to find the volume of one cylinder and add an infinite number of those together. So just like with the rectangle, each cylinder I draw is going to have a different size based on where I'm at along the function. Some will be bigger, some will be smaller, but there are going to eventually be an infinite number of these. So if I can find the volume of one cylinder that's just a representative, then I can stack an infinite number of those together by integrating. So let's try this one out. In order to find the volume of a cylinder then, just like with that cone, it's the area of the base, pi r squared, times the height. Well, we know that the height, or the thickness of this cylinder, is the same as the thickness of the rectangle that we were using. So the height of the cylinder is just some small change in x, dx. And since this came from that rectangle that was changing its height, we know the radius of the cylinder is going to depend upon which part of the function we're at. So we know that the radius is going to be f of x. And in this case, f of x is just x. Okay, so if we find the volume of one cylinder, that will be pi, the radius was x squared, and then the height was dx, so it's pi x squared dx. And now we're going to add an infinite number of these together from x equals 0 to x equals 4. So we'll integrate this from 0 to 4, pi times the radius squared times the height. Pi is just a constant, so I will pull pi out of here. I'm going to find the antiderivative of x squared. So that's 1/3 x cubed. I will integrate that or evaluate that from 0 to 4. So I'll do 1/3 times 4 cubed minus 1/3 times 0 cubed. 4 cubed is 64, so miraculously we got the same answer. Yes, of course, this seems way more complicated than just finding the volume of the cone. But like I said, it's not all going to be a cone shape. All right, so that's the general idea. This is what's called the disk method, because each of those cylinders is a disk. So we're putting an infinite number of disks, or an infinite number of cylinders, inside of this three-dimensional shape to find its volume. Okay, now let's go to a shape that is not linear. I just want to show you how we can generalize this process. So I've got a different function, or a different set of functions. Find the volume of the solid form by revolving the region bounded by y equals 4 minus x squared, x equals 0, y equals 0. And this one will be rotated about the x-axis. So let's make sure we understand. 4 minus x squared is a parabola, has a y-intercept of 4. Negative x squared means we're opening downward. The fact that we said x equals 0 and y equals 0 means we're bounding this in the first quadrant. So I'm going to get rid of the rest of my parabola because I don't need it. I only need the part of the parabola that's in the first quadrant. So I'll solidify my area. This is the region that's going to be rotated. And this is going to be rotated about the x-axis. Okay, this one's going to be a little tougher for me to draw, but what I'm going to do is reflect this first. And then I'm going to draw this circular bottom. Now, this is not an ideal image. So I have an app on my iPad, and I've already put all of this information in, and this app will show you kind of what this three-dimensional image is going to look like. So I put in, you can see here, I put in the function at the top, 4 minus x squared. The other function is g of x. Don't worry about that. That's 0. The interval from 0 to 2, because I forgot to show you that this intersects the x-axis at 2. So I said from 0 to 2. The axis of rotation is y equals 0, because that's the x-axis. And then don't worry about the number of intervals yet. So you can see down here at the bottom, this graph is exactly what I drew. Now, here's the cool part about this app. The cool part about this app is it shows this three-dimensional shape that was formed by rotating that two-dimensional area around the x-axis. So you can kind of see what that three-dimensional shape is going to look like, sort of. If I add a few more cylinders to it, if I just keep adding more and more cylinders, I get more and more accurate. Okay, so let's find the volume of this then. And we've kind of seen what it's going to kind of look like, but let's actually calculate it. So we're going to draw in a representative cylinder, and we're going to find the volume of that one representative cylinder. So I'm going to Just draw in one, doesn't matter where you do it. We already know the height because that's a horizontal line. The height is some change in x dx. And we know the radius is dependent upon where we are along the function. So the radius is 4 minus x squared. So to find the volume then of this solid, we will integrate from 0 to 2. We're going to take pi times the radius squared times the height. And now you can go through the process of finding the antiderivative of this. Now I will tell you though, you cannot use u substitution, because if u is 4 minus x squared, then du would be negative 2x, and we do not have a negative 2x in this. So your method in solving this would be to FOIL out 4 minus x squared, multiply it by itself, and then just use the power rule. Okay, I'm going to let you finish that one. Let's go to the next one. I'm going to show you a completely different setup. Now we've got two different functions. So the volume of the solid formed by revolving the region bounded by 4 minus x squared over 4 and g of x equals 2. So let's see, if we draw the parabola first of all. The parabola is up here at 4, and then it opens down in some way. Something like that. And then we also have the line y equals 2, or g of x equals 2. And we're going to rotate the region bounded by those two. So that region is here. That's what we're going to rotate. So I wish, in hindsight, that I wouldn't have drawn my lines so long. So I'm going to redraw them just to the point where I need them. So I'm going to draw the line y equals 2. This is not to scale, I'm just making this up because I'm not graphing it perfectly. And this is going to rotate around the line y equals 2. So here's the axis of revolution is what we call it. The axis of revolution is the line we're going to rotate it around. So it's going to look kind of like a football. This one's kind of difficult for me to draw, but it's going to look football-like. Oh. Would you like me to put it in the app? Let's try it in the app. So in the app, we've got 4 minus x squared over 4. That's the first function, so that's f of x. G of x is 2. Now the interval, because right now that's not what we need. Right now we've got an interval from 0 to 2. So we need to figure out from where to where. We need to figure out those x values. So let's go back here. We need to figure out where is this and where is this? Where do those two, where do we start and where do we end with all of our cylinders inside? Okay, so to do that, that's where those two functions intersect each other. So where does 4 minus x squared over 4 equal 2? Where do they intersect each other? So if I subtract 4 to the other side, I get negative x squared over 4 equals negative 2. Multiply by negative 4, x squared equals 8. If I take the square root, I get plus and minus the square root of 8, or plus and minus this 2 times the square root of 2. The square root of 8 is fine. I'm just going to leave it like that. So this value here where they intersect, still in eraser mode, is negative square root of 8. And this one is positive square root of 8. Okay, so let's go put that back in. The interval then will be the negative square root of 8. This doesn't let me do the square root, and at least I can't see how to do the square root, so let's just look at the square root of 8. Square root of 8 is 2.828, so I'll do negative 2.828 to positive 2.828. Okay. That looks a little more like it. That's the region that we're looking for. And then, I cut it a little too short. Let me put a few more decimal places because it's not quite football-like, but it should be. 2.82842 2.827.125. I just want it to look a little more realistic for you. 2.828.427.125. Okay. All right. Now it's going to look a little bit more football-like. It's still cut it off at the end, but you can kind of see, oh, I forgot, we're rotating around the wrong thing. We're rotating around the line y equals 2. That was a different experience. There's the football. There's the football I've been looking for. So that's the three-dimensional shape that it's going to be created by rotating this around the line y equals 2. All right, so let's finish this up then. Let's put in a representative cylinder. From the top of the shape to the bottom of the shape. Now we have to be careful with the radius. The height is no big deal. It's a vertical line, some change in x. The radius, though, is a little bit different. The radius is not just the function 4 minus x squared over 4. The radius is shorter than that. If I said the radius was 4 minus x squared over 4, that would be the length from the x-axis all the way to the top. That is 4 minus x squared over 4. But our radius is shorter than that. So can you imagine, can you think what this radius might be? This radius, in this case, is 4 minus x squared over 4, but minus this little gap. This is extra stuff. We need to take that away. So if we take away that part, so we'll subtract 2, that's the radius. So it's the top function minus the bottom function. Remember, that's how we did the area between curves, the top function minus the bottom function. All right, so we've got all the information we need now. We can integrate from negative square root of 8 to positive square root of 8. And this is pi. The radius now is 2 minus x squared over 4 squared times the height, which is dx. Same as the last one, you can multiply this out and then integrate from there. Okay, last one. We're going to go back to the second one we did, the graph of 4 minus x squared, but this time we're going to rotate it about the y-axis. So let me draw what that might look like. About the y-axis, looks like this, and if I make it circular, it's kind of like a beehive, if you will. That's the volume we're trying to find. So in this case, the representative cylinders are horizontal, and we're going to do a bunch of those, an infinite number of these. So it's kind of like when we found the area of something that was x equals. Things are going to be a little bit different. So first of all, the height is dy. So that means it's some change in y, some vertical length. So that means the radius must be written as a function of y as well. So in order to find the radius then, we know it has something to do with this function, this curve, but it's based off of the y-axis. So we need to take y equals 4 minus x squared and isolate x. So if I do x squared equals 4 minus y, and I take the square root of that, I get plus or minus the square root of 4 minus y. Now we're only dealing with this right-hand side because that's what's determining the radius. The radius is just from the y-axis to the right. So we're going to say then that x is the positive square root of 4 minus y, and that's what our radius is going to be. Okay, we know that these cylinders are stacked vertically, so just like this was in terms of y and this is in terms of y, the integral will also be in terms of y. So we're going to integrate from 0 up to 4 along the y-axis. Pi times the radius squared times the height, and the squaring the square root. And now this is just a power rule. Okay, I'm going to let you finish from there. You've got this integration part down.